FPGAs for convolvers and other glue collection logic. This is the first one where it was going to be a processor. I always called it a kitchen sink board because there's one of everything thrown on the board to support the FPGA, but it was good enough to support the back projector effort. I'm not going to go and tell all the back projector stories. The reference in my talk from HPEC that John Bloomfield did does describe all of that. But what happened is we did this great project. Everyone was happy, well, in the sense that we met our goals. The system performed. It did 3D reconstruction faster, more than an order of magnitude quicker than previous technologies. And then all of a sudden, everyone became disinterested because a clever engineer colleague at Mercury over the weekend saw that he could use a GPU to do the same thing. And as I'll show in subsequent slides, unlike the FPGA effort that we embarked on, the GPU code could travel and the FPGA code couldn't. We'd invested a lot of time in doing this spatial programming I talked about earlier, and we shouldn't have been surprised when Vertex 2 became Vertex 2 Pro, became Vertex 4, and that substrate architecture changed, that the code that we wrote at the switch box level didn't move, and the GPU code magically just did. So this chart right here shows back around 2003, 2004 in gigavoxels per second, the back projection speed. And the 2 points I want to highlight on this chart are the NVIDIA G70 and G80. So the original work that predated the G70, the first GPU code that knocked this off, actually took place in time, significant, maybe 2 years earlier than it's indicated on this chart. But the real surprise that FPGA design and the rest of this talk can only aspire to is that the delta in code from the G70 to the G80 and that factor of 2-ish, 2.5-ish performance gain up to the top right where the G80 is was 0. Nothing was required. And that is simply not the case at all when doing hardware design for FPGAs. So this little story that I tell about the back projector's failure was really not a failure, but rather a terrific insight, certainly from myself, in trying to understand how there's terrific value bottled up in code that travels, and there is potentially quite a lot of liability when one makes the commitment to a specific hardware microarchitecture. So I think I just said that. So what we're trying to get away is that if you're going to do this detailed, if you're going to exploit the detailed microarchitecture of an FPGA or any architecture for that matter, be aware up front of the consequences of that investment and that you may consciously be designing for non-reuse. You've been designing for performance. DataCube saw this before with x86s disruptively displacing their image processing, and now at Mercury we see this in the form of what I call application agility, or the opposite, applications being brittle, I guess. So is performance really inversely proportional to reuse? Certainly, I think I've given some anecdotal evidence to that effect up to this point, and we all can kind of reason about specialization inhibiting reuse. But as I started this presentation off with, performance isn't always the sole objective. What can we do to help this out? Oops, time check. Platform-based design. So when I got to this slide, I thought it would be a good audience participation point. Just if everyone could lift their hand up if they're familiar with platform-based design, and not lift it up if they might have heard the term but they don't really know what it means. Because I'm curious in this expert audience where we sit in that point. Couple of hands going, I'd say like 5%. So that's interesting. I highly recommend everyone Google platform-based design and find the Alberto Sangiovanni Vincentelli paper that's published describing same. Essentially, it's the notion of creating this point, a platform, between an application domain above and an architecture underneath. I've been in the church, as it were, of platform-based design for about 5 years now, and have tried to exploit it every way I can in Mercury's reconfigurable architecture. Another way to put it is effort is additive, and the effect is multiplicative. You cover a multiplicative space with additive effort. That's a good thing in engineering and in business. Since only a few raised their hand, I won't spend a lot of time on it, but I'll say if you're curious or question the sagacity of some of the decisions Mercury has made along platform-based design, go look it up, because there are a wealth of good papers and not really any bad papers that I'm aware of to be found. So component interfaces are platforms. In other words, back before when I was talking about like-to-like and like-to-similar and like-to-dissimilar, an interface can be a platform. And interfaces are sort of the linchpin of abstraction. Earlier I talked about control configuration, streaming message, and memory. I've drawn them as little colored circles here, and introduced this phrase, worker interface profile. I know lots of big sounding words, and I'm not trying to jargonify this, but just using our own terminology. So we have these profiles, or templates if you wish, that provide for our RTL-like IP well-defined adaptability and interoperability by virtue of reducing the choice of what a designer is going to use to have one worker talk to another. We've designed them in such a way that they're language agnostic, so in particular with regard to hardware design and the current sad state of things with RTL, whether they work equally bad or well with VHDL or Verilog. The semantics hold under hierarchy. And the value of these WIPs, or worker interface profiles, is that they give us some insulation by that platform from specific implementations. I'll give some examples in a minute. I think I just said this a moment ago. Why focus on the interface? Well, proven software methodology. Well, does that make it a good reason to? I don't know. But it's a time of change right now, because hardware designers, those filling the bit streams inside FPGAs, have pretty much had it with RTLs. The FPGAs from Altera and Xilinx are now sufficiently big that the decades-old VHDL and Verilog, or even system Verilog-ish ways of populating these IPs are running out of runway. And it's my own personal belief, it's absolutely insane to reason about chip level, let alone board or system level issues at a clock cycle level. That's not what designers are trying to do. In fact, it seems like a perfect job for some tool or automation to take care of that for us, so we could focus on bigger issues like how they compose together, or how I can change out one block without it breaking another. We need a hardware imagination language, and there are many of them out there. I feel bad in the sense that I only listed a single one. I'm currently quite enamored with trying to figure out the value proposition of an ESL called BlueSpec, which is a functional domain-specific language that looks like it's pretty good at this. There are dozens of other entries, other contenders in the space, and I think it's just a fascinating time to run out and, if cycles can be had, to try one of them out, to see if there's an alternative to this RTL. But we really can't reason about them unless we still have a way to stick them together. So again, this work focuses on the interface so that we can try out these different ESLs. The last sub-bullet there about not wanting to take any action that would prevent the use of a particular ESL cannot be overemphasized. So how do we do this? We decided at Mercury we need open standard interfaces to allow the partition. In our case, we chose OCP. We could have, for example, chosen AXI, but we wanted something that was open, so I guess that drove this decision. It's an interface standard. I think of OCP as an interface definition language. In other words, the 91 parameters that characterize an OCP interface are like Corba IDL. They define the interface. Is it a platform in the platform-based design sense? Yes, I feel. Is it a bus? Absolutely not. Biggest misconception about OCP, owing to its heritage, is that it's some type of shared media bus. You could make a shared media interconnect that has OCP spigots on it. We have, others have. But OCP is an interface. So In theory, it's this weightless edge between two nodes that has a specific protocol to it. So I say it has no weight of implementation, but the reality is to conform to any particular protocol, especially if you're in mindset A and the protocol is a different mindset, there is some weight of implementation. And lastly, on OCP, it's composable in this latency-insensitive fashion. Transactions can be composed into atomic events, and that's really vital. So earlier on, when I said it was crazy to reason about digital systems on a clock-by-clock basis at a chip or board or system level, so a transaction abstraction for an interface is a great thing, right? Because instead of thinking about click, 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 handshake and acknowledge, you're thinking about the entire transaction in a whole set. All right, picking up speed now. So how do we make these workers go together? There's this concept of the specifier and the implementer. Simple enough, right? The specifier at a higher level of abstraction, not wanting to the devil in the details about how many bits is the interface, thinking more mega samples instead of megahertz, specifies functional requirements. The implementer takes those requirements and she goes off and happily implements them. Sorry for the slideware, in the sense that you can't possibly, well, maybe you can read that from back there. Here's a block that some specifiers said would do gain and offset, and it shows three interfaces. On the top, there's a control interface that might set the coefficients, and there's a streaming vector in and out, and there's some XML-looking stuff that describes the property of the interface. So we've said everything that we want to from a system point of view about what this simple module will do, but we haven't actually implemented it. The implementer would go in and fill the bits in. Here I've taken two of those workers and composed them together, showing an assembly of workers, in this case two, where there's still streams of data coming in, going out, there's a local memory port, and there's control. So again, we haven't said anything really about implementation. We've said here is all about composition and how we've kept the specifier's role separate from the implementer's role. We're doing all of this in part to allow replaceability. So remember earlier when I talked about the back projector failing because we couldn't have the NVIDIA-like gain of simply plugging in a new graphics board when NVIDIA offered it. When Xilinx comes out or Altera comes out with a new chip, we can't just plug it in and work. That's what we're trying to get to. At least we don't want to take any actions that would preclude us from reaching this utopia someday where we can put in a new substrate and get our higher performance or lower power worker. Two slides here, quick, just concepts. The concept of arbitrary composability, which simply put says that adding a new element into the system isn't going to change the behavior of another one, and the linear effort property, which says the effort to add that block isn't going to be affected by the blocks that had previously been wrapped into the system. So where am I going with all of this? Ideally, we're going towards utopia. There's a zero cost at all of these interfaces. Component aggregation is easy. The communication costs are free, and the model is the same because so we can reason about it. But the reality is these interfaces have some weight. There's some cost to going to anyone's protocol if it's not your own. Aggregation can be tough. Communication's seldom free, and I didn't mean free in terms of just the time of flight, but just free in terms of managing communications as a resource. And there's a reason processor heterogeneity exists. GPUs and cells are great from some of their programming ISA aspects, but they're less great from their power standpoint, for example. So we view platform-based design in the sense of having multiple platforms, this constellation of different dots in different levels of the system as a way to wrestle this complexity. So here's an example that I'll tour through to wrap it up a bit that talks about one product that Mercury makes. It's a beamformer, a ground-based beamformer for satellite modem data, and it is a heavy FPGA application with a little bit of support by a GPP, and I thought I would talk a bit about how those various trades were made. Well, or how the selection of using, say, an FPGA and going back to the spatial programming method of of the back projector was driven by a particular requirement. So this is a system that's composed of many boards. The board's composed of many FPGAs and a processor, and the floor plan over on the right is a pattern we'll see in a little bit, which is essentially the inner loop of this big system. Here's a picture of the board. It has 9 FPGAs, 1 PowerQuick processor, which is, and we'll talk about the selection in a minute. So the bread and butter, the working core of the original version of this design is a complex multiply accumulate. It turns out that in beamforming you have data and you have these coefficients. They're complex weights, and the inner loop of this family of hardware looks a lot like a transposed form for a filter. It's really quite simple considering the complex task that the system is performing. And to the exclusion of virtually every other parameter, a driving fact was that we had to get a tera-op level of multiply accumulates happening to satisfy the throughput requirements. And that one point above all else, never mind having a good solution, the only possible solution we could have in this case, sort of making a custom ASIC, which itself has other issues, was to use FPGAs and to, just as we did 5 years ago with the back projector, build bottom up from this specific pattern and then craft the system around it, because no one was able to find a GPU or a cell or a multi-core GPP approach that would cover enough integer ops the way a mass collection of DSP-laden FPGAs would. So just to give some numbers, and for those of you in the audience who are FPGA aware, both the V4 and V5 design, in this case we selected Xilinx as our FPGA vendor. They have an SX family that has lots of DSP and BRAM elements. The original design actually had 100% utilization. We subsequently trimmed that down to balance the communication with the compute more fairly. But the pattern is essentially this transposed form fur, where the partial product bubbles up the top of the DSP chain, repeated 4 times over the V4 or V5. And it's a terrific value to Mercury and our customers in the sense that we're using these devices. In the V4 case, in both cases, in the V4 and V5 case, we're using the slowest speed grade at the fastest clock rate that the vendor guarantees the BRAM and DSP to operate at. And it's a terrific win, but it's kind of an odd egg application. So in the sense that you're being presented with, do a whole bunch of these complex multiply accumulates to solve the beamformer problem. Yes? Certainly. I'll work from top down, and again, time permitting, we'll come back to this at the end, but to fill in the point here, the diagram on the far right is a floor plan of, that looks like the V4 SX55, and you see roughly 4 quadrants populated with a colorful pattern that seems to be the same, if different colors, the same pattern in all 4, the bluish bit in the center being excluded. Each of those 4 sections utilize 100% of the DSP columns and BRAMs to implement a transposed complex fur filter, which performs the beamforming against the coefficients that we'll talk about momentarily. So the intent of the diagram on the right is to show the spatial or 2D structure of the inner loop, as it were, of the beamformer. The 2 diagrams in the center, well, the right one is a floor planner plot, and the left one, the right one is an FPGA editor screen grab, and the left one is a plot attempting to amplify the concept or drive home the concept that this bit here that's composed out of 4 elements is using 4 of these 100% utilized blocks to do one section of, or one kernel in parallel with the other 3. And lastly, this tiny diagram, or the small rat's nest diagram on the corner, is attempting to show the association between the complex coefficients held in BRAM and their specific BRAM, and their specific DSP targets, rather, in the column adjacent. So, for example, over here, this is our BRAM coefficients, and here is the DSP column, and this is simply showing the data flow, not the actual route that's shown over here between the BRAMs and the DSP. Good for now? Okay. So I said that when we went into this, we had to make some trades on processors. This slide's somewhat disconnected from that particular application. More in general, talking about processor strengths and weaknesses. GPPs, most familiar ISA, could be x86, might be PowerPC. It's familiar in any event. Depending on the device, it could have a wide dynamic range of floating point performance. Cell has a slightly less familiar ISA. Well, the PowerPC is familiar. The SPE isn't as much. But these SPEs get you into the 70 to 170 gigaflop range at the cost of hundreds of watts. GPU is sort of a similar bit. Maybe it's a little less familiar ISA, though some of the work NVIDIA is doing with CUDA is changing that. But it too is hundreds of watts. And then somewhat differently, you have the FPGA, where you can have this application-specific and, if you need it, reconfigurable ISA. This point that I made earlier about why FPGA, the integrated and specialized I/O, that as we'll see in a second with the beamformer, that combination of having just right I/O and just right processing in the same device really drove FPGA to be what else beside FPGA? And it didn't hurt that we were able to get sort of half tera-op performance out of these devices when we made the conscious investment to do that specialized spatial programming that I showed moments ago bit by bit. And icing on the cake is an order of magnitude less power than the other two. So I had wanted to show some detailed data, and our session chair, Ralph, had asked, but I found that people within my organization are understandably quite sensitive about trying to put a table together that shows for a particular application the trade space between these processors, because it would reveal how much or how little margin exists in a particular application. I think everyone in this room is probably capable of going to the vendor site, looking at Fmax, assuming a fully occupied schedule, and then saying, oh, it's certainly to order of magnitude levels, what's the throughput of this in gigaflops, or how many watts is this going to consume? But FPGAs kind of change this up because they're reconfigurable. You could potentially change it in time, although you don't have to. So we really need some benchmarks here, and I know there are a couple of fledgling initiatives to benchmark FPGAs in specific and heterogeneous processors in general. And I think that will help. I don't have a magic elixir here now to say, follow the axes of this chart, and where they intersect is the correct processor. Although maybe in years to come, someone will present here, and they'll have that for us. So back in the beamformer compute engine, as I've said several times now, it was pretty much a slam dunk. The inner loop complex max drove the selection of an FPGA device. In this particular case, we used a mixture of Xilinx SX and FX devices. The SXs to do the heavy multiply lifting, and the FXs for their SerDeses, because sort of the backstory when people look at the beamformer and go, God, that's really simple, and you get paid a lot of money to do that, is that the communications problem in the beamformer is as difficult or more complex, rather, and hence valuable than the actual multiply accumulate. Getting all of the data to appear at the right device, in the right board, in the right system, at the right chip, at the right time is a real juggling act, and we were able to accomplish that act by using an FPGA, in this case these FX devices that allow us to specialize our communication for the compute task involved. Lastly, but certainly not least, so someone has to do the SVD and QR behind the scenes at a much lower rate to come up with the coefficients. So there is a PowerPC on each of these boards that at a much lower rate than the data rate, than the wideband data rate, is calculating the beamformer weights. It happened to be a PowerQuick processor in this particular case. It was familiar, it was fast enough, and there wasn't risk there. The question had been asked, why not use one of the embedded processors on one of the Xilinx FX devices, I think, yes. And essentially, it didn't really add value. It would couple concerns. It's a perfectly respectable processor. I mean, maybe it doesn't have the weak floating point chops of the PowerQuick, but there was no value to having less latency. So it was one of those calls, and back to Stan's point about doing things that add value as opposed to because you simply could do them, it's clearly an example of that, where let's not do that because it doesn't add any value. So, in summary then, I hope, other than waving my hands around a lot, I've played back the concept that at different levels of hierarchy, this chipboard system pattern has been around for a while, will probably continue to be around for a while, and that in that this continuous change that's taking place necessitates or drives the need to be able to change things out at one level or another. We're continuously evolving. We're in an industry that's essentially moving forward continuously, and we need the ability not to throw everything out and start over, but to stick bits in. That heterogeneity is a requirement, and so it forces us to reason about different processors and the trades we make between them. And perhaps most importantly of all, that these platforms, these interface-centric platforms, help us wrestle the complexity. They're generally a good thing. It's a tool. But in and of themselves, to simply using it doesn't guarantee you success. It simply helps you reason about something that otherwise would cause at least my brain to blow up. So thank you very much.
So thank you, Shep. Good insights into your struggles, trade-offs. Quite fascinating, entertaining as well. I saw the passion in the presentation. I enjoyed it. Thank you. We have time for, I would say, 1 or 2 questions. Let's keep them to fairly short answers. And Shep is certainly available off to the side afterwards, and be more than glad to speak with you in more detail. See one question right here.
Yeah, my name is James Nichols, and I was wondering if you've taken a look at massively parallel processors such as PicoChip with their synchronous buses. And the other question was whether we can get a copy of today's slides.
So the last part of your question is easy, James. The slides are published in the proceedings.
Yeah, quick comment. So there were some additions made versus what we have in the handouts. The final version of the slides will be on distribution, not quite on the stick today, but we'll make them available. And
so there are many coarse and fine-grained reconfigurable processors out there. Rightly or wrongly, I have chosen at Mercury to try, much in the same way that our interfaces, we're trying to put some constraints. I have tried to put some blinders on, except where when another technology so obviously enables a market that is valuable to us, or a market that we want to move in. So essentially, I have consciously elected to be ignorant or know less about certain alternate processors, so we can make headway towards higher level of abstraction with the processors we're working with now. Specifically, to answer your question, yes, I'm familiar with PicoChip. No, I don't believe we're using them at this time.
Okay, great. Thank you. Yeah. Okay. Do we have another question somewhere?
Oh, come on.
There certainly was a question about the details of the floor plan diagram. We can certainly maybe spend some more time afterwards. One last question? Okay, great. I'll say thank you.
There's a perfectly good hand going up there.
Difficult to see.
Yes, you use the Xilinx with PowerPC.
Yes.
There was graphics processor. But have you thought about using TI, like DSP processor? What about Xilinx and the DSP processor?
That's a terrific question, and yes, not only have we thought about it, but we have a commercial product that marries FPGA and DSP, and like WiMAX is an excellent place where the two go together like peanut butter and chocolate. I mean, so I hope that my presentation today and its myopic view into a couple of applications didn't inadvertently communicate there's solely these specific associations like FPGA and PowerPC. No, in fact, what I hope to communicate is precisely the opposite. There are all these opportunities. I don't know of it just yet, but soon someday there'll probably be a slam dunk where someone puts an FPGA and a GPU and a cell together, hypothetically, to make some unique synergy that any two of those three couldn't do together. To pick three processors out of a hat. And in the specific case that you made, yes, we certainly have considered that. We have commercial ATCA product today that marries DSP and FPGA. Thank you very much.
Yeah, thanks for the question.
Okay.
Maybe I'll say we'll hold that question. I'm going to move on. Sorry about that. I'll make Shep available right offline. Say thank you, Shep. One more round of applause.
Okay. Thank you.
And I'd like to maybe a quick comment on time. So we're going to have one more speaker right now, and then we'll take a break of about a half an hour. Lunch will be at 1 o'clock. It's an early morning. We started early. Right after David's talk, we'll have a half an hour break, give you a refresher, get some daylight in here so we don't fall asleep quite yet. But say thank you, Shep. And David, welcome. Floor is yours. David will talk to us about the ASIC world, ASIC and ASSP world, really. Give us great insights into the struggles he goes through. He was commenting component selection and portability are drivers in his space as well. I'll let him go into more details in person. With that, I say, David, welcome. The floor is yours.
Thank you, Richard. Okay, I'll start off with a cough. Anyways, geez, it's bright up here. Is mic on? I believe. Can you guys hear me? Thank you, everyone. I'm going to go into something extremely specific, and maybe you'll see why in a second. So I'm going to talk about the ASICs to ASSPs, but I'm going to really just specifically the 3430, which is kind of the latest and greatest application processor from TI that I was involved in, and handsets in particular. So this is very, very targeted. There's all sorts of different ASIC worlds. So this is really ASICs as it applies to state-of-the-art handsets. This is very dangerous. Okay? Yeah. Okay. All right. The next thing is to advance the slides. There's lots of buttons up here. Page? Thank God. All right. So, framing the problem. These are boilerplate. It actually says boilerplate up at the top. So if you guys ever do foil presentations, boilerplate is stuff you grab from someone else that look like really nice slides, and you can talk to them. But I didn't put this together. But if you didn't know, one of the things in handsets is it's really an ideal application of really advanced process technology and kind of what we as IC designers or architects